Hi viewers, so today's topic is Lenz law. So before watching this video, please subscribe it, don't forget. So Faraday's law, what is the statement of Faraday's law? According to Lenz law, so statement of Lenz law, see here, let me please don't excuse me, why? Because I am zooming it, making big. Yes, according to the Lenz law, the direction of induced EMF or current in a closed circuit is such that it opposes the original cause that produces it. Okay, so what he is saying, the direction of induced EMF, how it is in a closed circuit. So actually let it is produced by a bar magnet, let outside from bar magnet, then this bar magnet can be opposed by the induced current which produce inside it. Alright, so by bar magnet you can produce the magnetic field, that magnetic field can oppose this one, that is called Lenz's law. Okay friends, again in the explanation you can understand clearly. See the diagram, see here, diagram is appearing very clearly. It is a bar magnet, it is a closed circuit. When bar magnet linked with the circuit, linked with the lines of forces, then around this coil what happens, magnetic field will be produced. And see that magnetic field is opposite, it is see the magnetic field means this circle also can act as one magnet, having the north south pole this side and north pole this side. This north pole repel each other. So how it is repel each other, let me explain in the explanation. Now see, the law is based on the principle of conservation of energy, right? Why it is the principle of conservation of energy? So here bar magnet is given. If bar magnet has to move forward and backward, it must contain certain energy. That energy is appeared here in the form of electrical energy. Okay, so that is why it is based on the law of conservation of energy only. Next, when the applied flux density B in a closed circuit is increasing, okay, when B value is increasing means number of lines of forces are increasing, the EMF or current induced in the closed circuit is in such a direction as to produce a field which tend to decrease the B. Okay, so one field produces that can decrease the B. So actually B produces this field and this field is decreasing the B. Okay, it is decreasing the B. So that is why it is called Lenz law. On other hand means otherwise, when applied flux density is decreasing, he in this case increasing, in this case decreasing, magnitude of current in a closed circuit is in such a direction as to produce field which tends to decrease the B, yes, which tend to increase the B. Here when the circuit, when the magnetic field is B value is increasing, it can decrease the produced field, and here when B value is decreasing, then produced field increases. So always works in opposite direction only. Thus the induced current is in a direction such that it produces a magnetic flux tending to oppose the original change of flux, that is tending to keep the total flux constant in the circuit. Okay, in this way the induced current, what it can do, it is in a direction such that it produces a magnetic field, and tending to oppose the original change in flux. Means original magnetic flux can be opposed by the produced magnetic flux. Okay, so then it makes them to do not change. So that is a constant. Suppose the north pole of a bar magnet. So here the diagram, in the diagram also given. Okay, see the diagram also. Suppose a north pole of a magnet is moved towards a coil. So see, it is a magnet coming towards the coil. Okay, so it is coming towards the coil. Which is coil here? It is coil. And what is round? This round is around it a magnetic field is producing. That is the symbol of that round. Okay, why? Because suppose it is a coil. Okay, when current flows through this coil, then around the coil what happens? Magnetic field produces. So that is shown here and here only. Suppose the north pole of magnet is moved towards a coil is connected to galvanometer as shown in figure. Here galvanometer is not shown, but imagine here. So it is a coil. To this coil, it is connected to the galvanometer. Okay, and the north pole of bar magnet is towards the coil. Okay, then what happens? See. Alright, as the magnet is pushed towards the circuit, an induced current is set up in the coil. Induced current produces its own magnetic field. What he is saying? It is a coil. Just now what I have shown diagram. North pole, south pole. So when bar magnet is coming towards it with a north pole towards coil, then here induced current will produces. Okay, induced current will produces, and this current again produces its own magnetic field. Here current produces its own magnetic field, right? Current produces its own magnetic field. Next step, in the next step what he is saying? Now the coil behaves as a magnet. Yes, when the current passes through the coil, it produces magnetic field and then it behaves as a magnet. When it behaves as a magnet, it must has the north and south pole. See, behaves as a magnet. The face to the coil towards the north pole of a magnet becomes a north pole. Okay, so see here once again, face of the coil, let it is a coil, and let this side is a face and this side is back. Okay, so let current is flowing like this. Okay, and when the current flows like this, then this around it a magnetic field will form. Okay, around it, and this side south pole can form and this side north pole forms. Already this side bar magnet kept with the north pole towards the coil and south pole away from the coil. See this north pole and this north pole. Okay, what he is saying? See once again listen, see the diagram. I am going to erase this one. Okay, let me draw here. It is a coil, current is flowing through the coil in this direction. Around the coil magnetic field forms, and this side is south pole, this side is north pole. Why? Because north pole is a face towards a bar magnet. It is a bar magnet having north and south. And now the coil behaves as a magnet. The face means this side. Okay, this side, face to the coil towards the north pole. So this side, so this side is face of this coil. Okay, towards the north pole of the coil towards the north pole of the magnet. It is a north pole of the magnet become a north pole. So this is a north pole of a coil. If it is a north pole of magnet, then this is north pole of a coil. If it is north pole of a coil, this side is south pole of a coil. Okay. Okay, so there will be a force of repulsion between them. Yes, right. So if it is north pole of coil and this south pole of coil, and this is a bar magnet having north and south, these two repel each other, right? Repulsion force between them. Due to this repulsion, motion of the magnet is opposed. Opposing property of body is simply Lenz law. Okay, so then this magnet cannot come this side easily. Okay, next, this causes change of magnetic flux in the coil. Thus the direction of the induced current is such that as to oppose the motion of the magnet. So how inside the coil current produced, you know, so in which direction it can oppose the motion of the magnet, in that direction only current will be produced. Okay, so conclusion is also given same thing. When the north pole N is approaching the coil, then magnetic flux is increasing through the coil, that is induced EMF and current are set up in the coil. This induced EMF current can produce again own magnetic field, and this oppose the north pole of Bohr magnet. Okay, and if it goes away from the, if the Bohr magnet goes away from this coil, then this side south forms and this side north forms, right? Then this south can attract the north of Bohr magnet, then Bohr magnet cannot go easily away from this coil. So like this it always opposes either forward or backward direction. This is called Lenz law. Okay friends, I think you have understood. Okay, so if you don't understand, please watch it again and again. Thank you.